So we've talked about equilibrium constants and how to make them. They are products raised to their coefficients multiplied together divided by reactants raised to their coefficients multiplied together. KEQ, equilibrium constants. We've said if they're greater than 1, it means products are favored. There are more products than reactants. If it's less than 1, it means reactants are favored, et cetera, et cetera. What else can we talk about with equilibrium constants? Well, the equilibrium constant is specific to the chemical reaction. So if I'm given this chemical reaction, what is the value of K when the equilibrium concentrations are this and this? Well, first I write my KEQ expression. It's a Kc because we're given concentration. So that would be O2 cubed divided by O3 squared. K is O2 cubed divided by O3 squared. Yep, done. To find the value of the equilibrium constant, we plug and chug the values they gave us. 1.5 cubed divided by 0.013 squared. Done. Plug that in our calculator and we get 2 times 10 to the 4th, 20,000. It's a pretty big equilibrium constant. It tells me there's a lot more O2 than O3 in this reaction when you run it here. But I could actually look at my equilibrium concentrations and know that there's a lot more O2 than O3. Yeah, okay. If I give you a different but similar equation, the coefficients are different. That means the exponents will be different in my KEQ. Excuse me. So that becomes O2 raised to the 3/2 power / 1.5 power divided by O3 to the 1st power. So I plug in the same values, 1.5 and 0.013, done, and I get 141.4, sorry. How can they be different things when I just said the K is specific? Well, because the K is specific to the chemical reaction, the K is different when the coefficients are different. The actual reaction is the same as far as it's O3 reacting to become O2, but when the coefficients are different, it makes the value of K different. So if I would have noticed that the bottom equation, the middle equation, is simply, the middle equation could be multiplied by 2 to give me the top equation, I could also see that if I have this K2, a coefficient becomes an exponent, right? Yeah. So if I square K2, I should actually get the same equation, the same value of K1. What? How does this work? Well, multiplying the equation by 2 would make this actually 2O3 and 3O2. Yeah? Square the K2. Okay. Put it in mathematically. If I just take this K number value and square it, that would really be 141.4 squared. And if you square 141.4, guess what you get? 20,000. So you could think of it as a couple of different ways. You could do it, if you have these top 2 equations, you could realize that this second equation is 1/2 of the original. So you could raise the original to the 1/2 power, also known as taking the square root. Or you could do it the way we did it, where you just plug and chug and say this raised to the 1/2 divided by that, looking at my coefficients. Yeah. Sometimes we will be given different equations and told find different KEQs. And whether you do it the way we talked about it, moving from the first example to the second example, or whether you do it the way we talked about it, moving from the second example to the third example, doesn't matter. I feel like I talked a lot about that just now, and I didn't really say a whole lot, but it is what it is. I actually already made this video twice already, and things went awry, so you're getting the ramblings of the third attempt. I apologize. So what else can we do with KC, KEQ stuff? We can do problems like this. When 3 moles of I2 and 4 moles of Br2 are placed in a 2-liter flask, what is the KC? There was one more little nugget of information in there, but I skipped over it. If you're working on an assignment for me and you are struggling to know what to do, absolutely you should write the KC expression for this. You will get points from writing the KC expression. So that's concentration of IBr squared divided by Br2 times I2 concentration raised to the 1st power each. Done. KEQ expression. It's a KC because we're talking about concentration. So then what? Well, apparently we want to know the mathematical value of KC. But in order to find the mathematical value of Kc, we need to know the equilibrium concentration of IBr, as well as the equilibrium concentration of I2 and Br2. How do we find those things? Well, I'm told the equilibrium number of moles of IBr is this, so 3.2 moles divided by 2 liters gives me 1.6 molar IBr at equilibrium. But these values up here are not equilibrium values. These values are initial numbers. They are the instant that you combine the things together, not after equilibrium has been established. But we're going to need to know that initial concentration too. So let's take our 3 moles and divide by 2 liters to get, my ink is not working today, I'm sorry. 3 moles divided by 2 liters to get 1.5 molar I2, and 4 moles divided by 2 liters is 2 molar Br2. All right, what are we going to do with that information? Well, let's write out the reaction again and draw out an ice table, a rice table, an ice box, depending on who taught you what previously as to what they might have called it. I call them rice tables because I want you to know that the first line is always the reaction. The second line should be initial concentrations. So we just said that 3 divided by 2 is 1.5 molar I2, 4 divided by 2 is 2 molar Br2, and there's no product in the beginning. That instant that you put these things together, no product. The equilibrium concentration of IBr was told to us, / the equilibrium number of moles was told to us, and we said that's a concentration of 1.6 molar. But we were not told anything else in our sentences on the previous slide. So where the heck do we go from here? I said we're building an ice table, a rice table, an ice box, whatever you want to call it. That C stands for change. So the initial row is always in terms of molar concentration. The equilibrium row is always in terms of molar concentration. And the change row is in terms of X. What the heck do I mean? Well, we're going to lose reactants as the reaction progresses, and we're going to gain products as the reaction progresses. So that means this can be minus X plus X. However, they don't decline and increase at the same pace, at the same speed. What the heck? This has a coefficient of 1. This has a coefficient of 1. This has a coefficient of 2. For every I2 that's consumed, we create 2 IBRs. So we have to account for that in our change row. So that means I'm going to gain 2X in my IBR column. I'm going to lose 1X each of I2 and Br2. Okay, where do I go from here? If I look at this completed column, I know that 0 plus 2X equals 1.6. Solve for X. 0 plus 2X equals 1.6. Again, my ink is not working, so I'm just going to repeat myself. That means 2X equals 1.6. Divide by 2, that means X equals 0.8. So if X equals 0.8, I can go back and fill in 0.8 here. 2 minus 0.8 is 1.2. 1.5 minus 0.8 is 0.7. So I found my equilibrium concentrations of my 2 reactants based on solving for X. We will do so much solve for X reactions in this class. Please note, all numbers in a rice table are molar concentration. That's kind of a deal. So there's our KEQ expression, our KC expression. If we fill in equilibrium concentration values, we get this, 1.6 squared divided by 0.7 times 1.2. Do the actual math of that, and we get K equals 3.05. 3.05. So what's favored, products or reactants? Hopefully you'll get that right. Goodbye.